Hi, everybody. Good afternoon, morning, evening, wherever you're tuning in from. Thank you so much for joining us today. My name is Dr. Nienke Kans, and I am an application scientist here at Protochips. Actually, all of us here joining today are from Protochips, but I'll have a chance to introduce all of our speakers today as well, because today we are kicking off this webinar series surrounding our new in situ system called Triton AX. As you might have already heard, this newest solution is a first heating and cooling electrochemical system for the electron microscope. As this is such a new solution on the market, we wanted to start off with a webinar that introduces the product first and also show you what kind of applications can be researched. So this webinar today is split into two sections. There is a shorter section presented by our Senior Manager, Marketing and Product Management, Jennifer McConnell, followed by the longer section presented by our product applications engineer, Kate Morozak-Stevens. So Jennifer will give a short presentation introducing the Triton AX system, and Kate will go over some applications examples, including freezing of water, copper plating, and also dose at sub-zero temperatures. Before I introduce the two stars of today's webinar, I would like to make a couple of household items to cover. First of all, everybody is muted because we have a quite large audience size and we don't want to have any unintentional interruptions while our presenter is giving their talk. If you have a question for her, please enter it in the questions box on the GoToWebinar panel, and we will address all the questions at the end. So from both presentations, all the questions will go at the end of the talks. There will also be a short survey that pops up after the webinar, and we would really appreciate it if you fill it in because it helps us with future webinars and understanding your preference. And if you need one, a certificate of completion will come into your email after the webinar if you're looking for it. So, okay, without further ado, let me tell you a little bit about our first speaker, and then I'm going to hand the mic off to her. So Jennifer McConnell holds a bachelor's in chemistry and a master's in forensics chemistry, with a strong experience in analytical chemistry. Since joining Protochips in 2018 as a product specialist, she has advanced to roles in product management and then recently marketing, leveraging her technical expertise to drive product strategy and marketing growth. So Jen, the mic is to you. I think you already have some slides up. Good luck with the presentation and everybody enjoy.
Thank you so much, Nienke. Hi, everybody. Thank you so much for spending your time with us today. We really appreciate it. We are, as Nienke said, introducing our newest in situ solution, Triton AX, the heating and cooling electrochemical system for TEM. And so my part of the talk today is I'm going to give a quick introduction to Protochips in case anybody is new here, but I'll keep it short, I promise. I'm going to just cover which application areas are primarily relevant for Triton. And then again, I'm not going to show any real data because that is what Kate is going to be showing in the second half of this presentation. So I'm going to save all that for her. But I'll touch on which application areas make the most sense and why. And then we'll take an in-depth look at the Triton AX system, which is what you're here for. So let's go ahead and get started. But I just wanted to, some of these photos here, just to let you know, came from the development process. During the development process of Triton, worked very closely with Professor Yao Yang of Cornell University. I spent a lot of late nights at the microscope, not only testing the system, but doing experiments that prove that it works well for the different applications it's been designed for. So thank you, Professor Yang, for all of your support as well. So my quick introduction to Protochips. We're based in Morrisville, North Carolina, which is the Raleigh area of North Carolina on the east coast of the US. We have been in the in situ TEM business for almost 20 years at this point, and we've got employees and offices around the world, in the European region, in the Asia region, to support our growing researcher base across the world. The company did start in 2002. We introduced the first MEMS-based heating holder in 2008. So we were first to the market with a heating and biasing style holder. Since then, we've introduced several reproducible ways to create in situ environments in the TEM, right? So more realistic environments your samples from gas and pressurized environments, going up to 1 atmosphere of pressure, in gaseous environments to liquid environments where you can do heating or you can do electrochemistry. And then, of course, you can apply high temperatures, heating, quenching, electrical in the vacuum of the TEM as well for just ranges of different applications, which I'll touch on everything at the very end, just so you can see, see our portfolio if you're not familiar with it. And my last couple introductory slides, just want to emphasize that, at Protochips, when we design new systems like Triton AX, we're looking at creating more than just a holder. It's more than just a holder that can do a bunch of really interesting stimuli. We're looking for a solution. We've got 3 main goals when we design a new system. Goal number 1 is ensuring that we're helping you scale your experiment from the bulk to the nano. In many research areas, TEM, if you're using TEM, it's not your one and only analysis technique. Anything you gather from the TEM needs to complement whichever other bulk techniques or larger scale techniques that you are performing. And so it's really important to us to work with the community to understand, how do we scale it? What materials do we need? What does good data look like? How does the data differ when it goes into the nanoscale or when it's being taken at the nanoscale? So that's really important for us, Triton included. Accelerating productivity. TEM is not a high throughput tool already on its own. And so we're looking for ways to take some of the more, the required tasks, but you wish they were in the background and you didn't have to focus on them. And trying to support that with software, support it with sample prep, to streamline things and accelerate your productivity. And then, of course, fostering collaboration and discovery. Most researchers, you're working with partners across the world more often than not. And with TEM and in situ TEM, your data sets are large. How do you share that data? How do you look at it in a standardized way and have productive conversations with each other? So we also look into those areas as well to see how can we foster this discovery process and collaborative process. And, in short, in order to do those 3 things I just mentioned, we have to focus on the entire workflow when we develop, my goodness, I haven't had coffee yet today. So again, not just a holder that goes into the TEM with stimuli, but sample prep, really important to consider for reproducibility and validity. Data management and data processing. How do you find, how do you understand what you have just captured? And draw conclusions and next steps from that. So we focus on the entire workflow. The Triton AX system has been added to our in situ family that you can see here, and our entire in situ family communicates with and is supported by the AXON software platform, which opens up a line of communication between all the instruments in your lab, such as your TEM and your in situ systems. And then the AXON platform also supports your data review and sharing with an AXON Studio module. And we'll touch on all of the pieces here, within this presentation, so you know how they all work together. But between data collection and aggregation, understanding the dose that you're applying to your sample, working with high frame rate collection, and then data processing, the AXON family supports every in situ product, again, to accomplish those 3 things I mentioned: scaling bulk to nano, accelerating productivity, and fostering collaboration and discovery. Okay, let's get into it. This is what you're really here for. Triton AX is our brand new in situ heating and cooling liquid electrochemical system. This is one of the many AI photos we had floating around the office during development. I know this is a light microscope, but I just love this one and love to share it. In summary, Triton is a new liquid cell system for TEM with a wide temperature range, so from -50 degrees C to 300 degrees C, that can be applied during electrochemical experiments. Why would you want to? There's a few different reasons that this makes sense and that this temperature range was chosen. One, to create an environment that's more relevant to different materials, a more operando style environment. For instance, think of studying batteries for electric vehicles in cold weather climates. We need temperatures that are more relevant to the situation to better understand how to move forward with that research. To speed up or slow down reactions to study those dynamics or kinetics more easily, right? So if you've got a very fast reaction, cooling it will help to slow it down, and vice versa, of course. If you've got a slow one, heating it will help speed it up so that you can study these reactions in a more appropriate amount of time. And then also to mitigate beam damage to your sample and the liquid media. And this is relevant to cooling specifically. So for all of these reasons, having a temperature range like this really supports different areas of research. Which areas of research are most relevant? I'm sure some of you kind of see yourself already with these capabilities. You're looking at them and thinking about what you can do with them. But we developed the system from feedback from the community. It wasn't just something we thought would be really fun to make. From the battery community, we had a lot of feedback, again, want to see cold weather climates in the TEM. How can we do that so that we can simultaneously charge and discharge the battery in a cold weather style climate? So we added the -50 temperature range for that. Electrocatalysts typically are operating at higher than room temperatures, 70 degrees C to 90 degrees C or so. Some are a little bit higher. And so again, we had a lot of feedback asking for more relevant temperatures for studying electrocatalysts, in situ in the TEM as well. Corrosion. So corrosion is one of those processes, like corrosions of steels and alloys, let's say, very, very slow process. You may be sitting down at the TEM if you're in its natural time frame, days, weeks, months on end. And so if you add and increase the temperature, you can make that reaction happen a bit quicker. Nanomaterial chemistry, another big area, because we've had a lot of feedback and requests. Researchers want to watch the nucleation and growth process of their nanomaterials that they're synthesizing. And there's a lot of them that are synthesized in organic media. They take high entropy alloy materials, for instance, are synthesized between 200 and 300 degrees C in an organic medium. We had a lot of feedback looking for higher temperatures to watch this synthesis process of nanomaterials. And then, of course, beam sensitive materials across the board, whether you're doing electrochemistry or not, and you just want to image your beam sensitive material in a liquid media that's relevant, the cooling is going to help with that aspect and help you image these types of soft materials and such with longer periods of time. So let's take a look at it was a quick overview of the applications because my time is limited, and Kate's side of the presentation, I'm sure, is going to be more fun than mine even. But let's take a look at the system itself. How does it work? How is it applying these temperatures? What does it look like? So again, reviewing the key capabilities for the system here, you're performing quantitative electrochemistry from -50 degrees C up to 300 degrees C. And again, you don't have to do electrochemistry. You can just do temperature in liquid. You can apply that temperature in liquid without the electrochemical stimuli too, which broadens the flexibility of the system. It has been optimized for STEM and EDS measurements in liquid. You don't have to remove the liquid in order to obtain really nice STEM images to help control the dose or to obtain EDS maps. You can if you want to, of course, but you don't have to. You can keep that true in situ environment while you do those measurements. The entire system's been integrated with our AXON machine vision software family for image stability, dose management, and metadata synchronization. And then we have made the design easier to load in a glove box due to the nature that, especially with batteries, you've got a lot of air sensitive materials. And so we've tried to make it a little bit easier and more streamlined to load in a glove box as well. So how do you create that liquid environment safely in the TEM in the first place? And so here's what the holder assembly looks like in order to create that cell of liquid. If you're familiar with our products, you're going to see a lot of familiarity here. It is a self-aligning assembly where every piece kind of fits into its own slot. So it's pretty straightforward to understand how to put together. And obviously hermetically seals once assembled. So if we look at this again, we've got a single sealing gasket. The one gasket versus multiple O-rings tries to help prevent additional leakage points, minimize the areas where you could get a leak. You've got a small MEMS device that goes in first, which I'll talk a little bit about the specific design. And if you're, again, not familiar with in situ TEM, each of these MEMS devices, these two chips where your sample will go in between, each of them has what we call a window where the electron beam is going to go through from the TEM, and that's where you're going to do your imaging. So you can see the window here on the small chip. The one on the large chip's a little bit harder to see. The large chip also has all of your electrodes and your heating coil. Kate's going to show you a closer look at that later. But as you assemble, your sample will go in between. Those two windows are going to automatically line up. You don't have to necessarily use additional tools to complete that alignment. And so it helps with training and streamlining that training process, streamlining the assembly process. The goal is to spend less time with your hardware, get it in the TEM so that you can actually perform your experiment. And then we've got a new probe design. Again, if you're familiar with our previous products, a new probe design to help increase chemical robustness. Now, the first step in these types of experiments is to ensure the electrochemistry that you're obtaining is actually quantitative. If it's not quantitative, then the images and the story you have to tell don't really make a lot of sense. It needs to complement whatever bulk experiments that you would be using them with. And so in order to enable quantitative electrochemical analysis, we've ensured that you've got different electrode materials as options. So the working electrode can be carbon, glassy carbon, or platinum, which again, very comparable to what's used on the bulk scale. The design of the chips and the design of the holder ensure controlled liquid flow for the replenishment of the electrolyte. You have to walk a very fine line with liquid electrochemistry and make sure you have enough electrolyte for good signal to noise, but you also want to control the thickness of it for better imaging resolution. And so with our chip designs and our holder design, you're able to do that. Mitigation of the interference from gas products. Some of these experiments produce gases, bubbles, and sometimes you accidentally produce bubbles. You're not supposed to. If you do, you need to be able to remove them, which again, the design of the chips here enables the removal of those. Once you have the quantitative electrochemistry side, now let's go ahead and add another variable of temperature. When you're going up in temperature, let's say, so you can see our temperature coil here. This is our patented frame heater technology, which you can technically only legally buy a system with an embedded coil like this, with this frame heat technology from us here at Protochips. But we've embedded it in the chip so that the entire top chip heats up, and there's enough power to heat all the liquid in the cell. So you have a nice uniform liquid layer, even as you're flowing. With the Triton AX system, you can ramp your temperature. Your ramp rates go up to 1 degree C per second. So that's both up and down in the heating and cooling direction with ultimate precision of 0.01 degrees C. Now, as we get into the cooling side, I'm going to explain why you have this unlimited interrupted imaging once you're at temperature. But again, once you've got the quantitative electrochemistry side, we're now able to add a nice, stable, uniform temperature to the liquid in the up direction or the heated direction. And Kate is also going to talk about this here, the importance of the channel isolation to eliminate or mitigate crosstalk between your electrochemistry measurements and your heating measurements. But I'm going to let her get into that later, but that's a very important specification to make sure you're evaluating when you look at a system like this. To expound upon the electrochemistry just a little bit that's happening during those temperature changes, your working counter and reference electrode are all here patterned on your chip. You do have the option of using an external standard reference electrode though, something like silver chloride or saturated calomel, which will help compare to bulk experiments even more seamlessly, because that's what you're typically using on a larger scale or a benchtop scale. And again, I mentioned the multiple electrode options for the working electrode, such as glassy carbon or platinum. And all of them have been optimized, again, the design and the orientation of them for EDS measurements during the experiment. From the gas mitigation side, again, you may be creating bubbles either because the chemistry generates them, or you may do it on accident as you are trying to optimize your conditions. And the design of that smaller MEMS device, we call these our flow management chips, helps to create a flow channel through the chip that just sweeps away the gas bubbles as they're generated. You can see that the window area here is at a higher elevation, let's say, than the trench where the bubbles and such will be flowing through. This is to keep your imaging area, the liquid in that area, thin, but we've had thicker liquid around, which will help flush the bubbles out much more readily as we flow, and it will also keep a more bulk-like electrochemical environment around your reference and counter electrodes, again, helping to emphasize signal to noise. Now, from the cooling aspect, we do cooling a little bit differently. This isn't a cryo holder, keep that in mind. We're not trying to freeze the liquid. We're trying to create cooler environments. And so we are using a Peltier device for cooling, so a thermoelectric cooler built into the back of the holder. And it's going to cool down to minus 50 degrees C is your limit by cooling through the holder, and it cools down the entire tip of the holder. Now, you don't have to go to that minus 50 degrees C. You're not bottoming out like you would with cryo, where you have to go usually to the coldest temperature. You do have control over that temperature, and I'll show you how the cooling works together with the heating to do that modulation. But because we're not using liquid nitrogen, you don't have a dewar to refill, hence the unlimited imaging, unlimited stable imaging as well. So to modulate the temperature, you'll run the Peltier device, so the cooling will take place, and then simultaneous to that, the heating coil, the frame heater technology I was talking about earlier, will compensate and help modulate the temperature if you're trying to go to minus 25 or minus 30 or 0 degrees, somewhere in between that range. And so the two will work together to then heat from the cooled temperature and help you modulate in the middle of your experiment to whichever temperature you would like to call for. And so that's the operation of the Triton system itself. Let me touch on the software and some of the software management that's working with it as well. What we've noticed too during those experiments using our dose software was that between the heating and the cooling temperatures, at the cooler temperatures, we were actually able to increase the dose. I don't know if you're able to see, but we are able to increase the dose up to 4 times that than what we were able to do at the higher temperatures. Because if we use this dose rate at the higher temperatures, what would have happened is we would have de-wet the cell. We would have pushed all the liquid out of the cell, or we would have automatically started crashing out electrolyte or crashing out copper from the electrolyte from our different experiments. And Kate's going to cover this experiment in a little bit more depth, but using our dose module, we were able to understand and review the dose data and see that even during our experiments, which were not in-depth, let's say, research experiments, you could see the initiation of the fact that the cooler temperatures really do help mitigate some of the damage that the beam can cause. Now for the software, I think, if you're not familiar with our AXON machine vision software, the goal of the software is to help you perform these tasks that, such as stabilization, note-taking, alignment of your notes with your images that you would kind of wish would happen in the background. It will do that for you so that you can focus on your experiment itself. And so an example here, the Triton synchronicity software, let's say if you remember from my map, the synchronicity software was in the lab with you, and it was a long bar in my product map. It's communicating with the TEM and it's communicating with the in situ software so that you, as the microscopist, you can sit here and observe your experiment, which in this case is undergoing a temperature range, a temperature experiment, and it's going to do stabilization, note-taking of the parameters as they change, and alignment of all of that with your images for you. It's calibrated to your TEM so that it will sample the images as the experiment is occurring, analyze the movement of the sample itself, and then communicate back to the TEM to physically correct for any drift or any movement that's occurring. And you can see that here on the microscope software. You can see this sample, it kind of starts to move away and then come back and move away and come back. And that is the synchronicity software correcting for movement, while Kate, who's going to be presenting in a moment, can focus on what's actually happening with her sample in a completely drift corrected format, all of it live though. So it's physically correcting live for you. Then once you're done with your experiment, you can take the AXON Studio software, which was on the right side of the product map, to help you analyze that data, visualize it in a timeline with all of your parameters, with all of your metadata, so that you can understand what you have collected. And Studio is free, so you can share this with any of your collaborators. This falls into that fostering collaboration bucket for us. Share it with any of your collaborators. they can see the exact same set of data you do. They can see all the parameters because everything's aligned and recorded that you do. And you can have a really productive conversation about what was just collected. So you've got live physical drift correction, live note taking, metadata alignment, and you've got data visualization with Studio here, all working with the Triton AX software. Or excuse me, all working with the Triton AX system. And then to calculate those dose measurements, the dose module for the AXON software is what was used there. And the module comes with this Faraday cup holder, which allows you to take beam current and beam area measurements for TEM and STEM mode, and you set different imaging conditions that you may use. Use the Faraday cup holder to do the measurements under those different conditions and create what's essentially a calibration curve for your microscope. And that's all stored in the AXON software as well. Then you would remove this Faraday cup holder from the microscope and put the Triton holder in, or you could put one of your standard holders in, and you would have automated dose calculations and automated dose alignment with all of your images. Again, all of it recorded for you. Again, very important, especially in liquid cell for reproducibility. You get these colorized maps that help you visually see how much dose has been applied on a pixel by pixel basis. And you also have, I'm running on my time. You also have, it remembers, because of the drift correction algorithms it's using, it remembers where the dose has been applied before. So if you take a look at this video, which I will play through pretty quickly, you'll see what will pop up here is a dose atlas, which is a low magnification view of the stage. So you can see the colorized maps here show where the dose has been, where it's been applied at certain levels, and you can see all the metadata here being applied as an overlay on the image. Then you get this dose atlas. This is where we are. This is our field of view right here, and it's colorized as well to show that you have been there. If you want to go somewhere else on the stage that has not been touched, it's very easy to see where that is because there's no colorization anywhere else. You can double click, move to a new area. It will blank the beam as you move so you don't just shower everything with dose. And now you can see where you were before. It's going to remember that for you. It's going to keep that history. If you go back to that area later, it's going to just continue to accumulate the amount of dose that's been applied there, and you've got a complete history. And so that concludes my introduction to the Triton AX product with the machine vision software aspect. I know it was a bit quick, and so if there's any questions, please feel free to put them in the questions box. But Triton AX is just one piece of our in situ solutions family, from Fusion AX, which does heating and electrical characterization in vacuum. Poseidon AX is our original liquid cell for mixing, for heating, for liquid imaging, and then our atmosphere AX system for gaseous pressurized environments.
Thank you so much, Jen. Thank you so much for this wonderful summary of the Triton AX software and the Triton AX hardware and everything together. So let's see if we can get Kate's camera back online while we are switching the screens to her as well. And in the meantime, while the screens are being switched, I will introduce Kate here as well. So this is the second part of our webinar, a little bit more technical for you guys, and this will be done by Kate Marusak-Stevens. She has a bachelor's in material science and engineering from North Carolina State University, where she did her undergraduate degree with Joseph Tracy, working on magnetic nanoparticle synthesis and characterization. Then she continued on to Duke University, where she did her master's in biomedical engineering and her PhD in mechanical engineering and material science, working with Stefan Zauscher. And during her PhD, she worked on E. coli precipitated cadmium sulfide quantum dots. She joined Protochips in 2018, so it's already a while back, and is now in the new product development team, where she is a major contributor on all our product development activities, including Triton, where she did so much work. Kate, we can see your screen, but we're seeing it in presenter mode at the moment. So maybe you should share the other one, if that is possible. Yeah, that's perfect. Great. So without further ado, Kate, can we hear you just to make sure that your audio is working? Not yet. Yeah, no, it's
and
working.
I'm trying to minimize this guy. Sorry guys, first time using my first time using GoToWebinar. So just be
And
patient.
again, everybody, the questions I saw that there was already some questions, but they will be handled at the backside of the webinar. So Kate, go ahead. Thank you so much.
Yeah, thank you for that nice introduction. Can you guys see, you can see my slide, not my,
Yes.
okay, cool.
It's perfect. Mm-hmm.
All right, so yeah, Jen gave a really nice introduction to the system. I'm gonna go over some data that we collected both as a product development engineer, testing the product, making sure that it worked before we started selling it to people, but also in collaboration with Professor Yao Yang at Cornell. And so without further ado, there we go. So today I'm going to go over some slides on observing the freezing point of water, some copper electrodeposition while heating and cooling, temperature mitigation of beam damage, and then a few important considerations when using a system that does heating and cooling and electrochemistry, as well as a slide on future work. So before we begin, I know that you got a bit of an introduction from Jen on the e-chips that we will or that we do offer with this system, but just so that everyone here is aware of what we use in these slides, we used both the temperature control e-chips that don't have any electrochemistry electrodes on them, so it's specifically just for heating and cooling, as well as electrochemistry chips with a platinum working electrode counter and reference. Those aren't the only options that we have, but those are the only ones that we use in these slides here. And then for small chips, we used our flow management chips, our standard flow chips, and we also have a slide on micro-well chips, which I'll talk about more later. So just so that everyone here is aware, I tried to put which e-chips we used on the slides themselves, but there are many more combinations available than what you're going to see here today. So we're going to start with observing the freezing point of water. Again, I am in product development here at Protochips, and so I'm not a true researcher anymore. My job is actually to make sure that things work and that nothing breaks, and that when we provide our customers with a product, that it's something that they can feel is not only safe, but also accurate and works really well. So what's a low-hanging fruit for confirming that we're actually cooling our sample? Freezing ice. So one of the first experiments I did, and my video isn't playing here, there we go. One of the first experiments that I did was cooling cooling water to watch the phase transition of liquid to ice, to solid. So I did this, was a little bit surprised when we went past 0 and still didn't see this this freezing occur. And here I'll start back over here. What you see there, that corresponds with the spike here in temperature. So we actually see this phase transition occurring at somewhere around -8 degrees Celsius. An interesting discovery, which I didn't know at the time, but makes sense once I thought about it, is that freezing water is exothermic. You're actually forming new bonds, which will release energy in the form of heat. And because our chip is a closed loop temperature control, we're not only finely controlling the temperature of your sample, but we're also measuring changes at the temperature, at the sample. And so when I was digging back through the data and we saw these spikes, that was very technically interesting to me. But we had this question: why didn't my water freeze at 0? That's where I was expecting it to freeze. And in addition to that, I don't know if you can necessarily tell, but these aren't very, there isn't a lot of great contrast in these images. I wanted slightly better resolution, so I decided to also thin my liquid out a little bit better, a little bit more. So I decided to repeat with a slightly thinner liquid. Oh, just a phase diagram in case any of you can't remember your chemistry from chemistry course from back in the day and phase transitions and stuff like that. the point of freezing for water is here, 1 atmosphere, but with changing pressure, you can have different freezing points. And so that was another suspicion that I had. Okay, is it maybe that the cell is pressurized differently from atmosphere? So now the thinner liquid here, repeat, repeat, repeat. So let's do it again. This time I had a slightly thinner liquid layer. I actually did measure with eels these liquid layers at the corners. And so this one was about 560 nanometers of liquid thickness at the corner that you can see here in the image. And here we go. This one was interesting because you can actually see the particles moving at the very beginning, wiggling around. Then they slow down until there's just maybe this little guy is the only one who seems to be moving. And then bam, we freeze. And when that freezing occurs, there's a shift. And then so everything sort of moves because there was a huge phase transition. And then after that, I'm sort of looking around. So I start moving the stage because I wanted to explore. But we see this, boom, again, there we go, liquid to solid. And again, it happened at not 0, -10 degrees this time, and had an exothermic reaction. So, okay, we know for sure we're cooling. We see things slow down. That makes sense. They were probably moving in the first place because of my beam. But why are we still at -10 degrees? So do it again. That's how you got to keep repeating and repeating and repeating. So this time I went even thinner, also selfishly because I was kind of hoping to do some diffraction on the ice after it had formed. And this time you'll see the video, I go down in temperature, we freeze, spoiler, and then we start to warm it back up and you'll actually see it melt. So there's the freezing point. I was changing my focus. We see what looks like either crystals or bubbles growing. And in a second here, I forgot that I had this. This is the only slide that I have this animation on. There we go. In a second here, we'll start to warm it back up and we'll actually watch the ice melt. You see those facets kind of smoothing, and boom, our cell has melted, or our ice has melted and left the chip. Okay, so at this point, we're wondering, all right, that's three different experiments where we froze with 3 different liquid thicknesses. Is there a trend between thinner liquid and lower freezing point? So what's the thinnest layer, or the least amount of liquid that I can look at? Microwells. So when I say microwells, you can sort of think of the 96 well plates where you would fill your well plate with whatever solution is you're looking at, and there's like a meniscus at the top. That's kind of what, or that is essentially what these microwell chips are, except they're micro-sized. So I used the 4x8 microwell small chip. I still had, the top chip was still a standard heating only Triton chip because we wanted to control the temperature. And here we start going down and down and down in temperature. And you'll notice I get all the way down to -25 and I never see a spike. I was also imaging during this, but the video is very boring because nothing seems to happen. No huge phase transition occurs, nothing dramatic. It's just, just liquid and nothing seems to change. By the time I got down to -25, I decided that I wanted to go home and wrapped it up and said, okay, we need to look at the literature and see what's going on here. But I will show, when we looked at the literature, we found this paper from Hokkaido University where they actually made their own Peltier holder. And they went all the way down to -12 degrees. And from what I can tell from the paper, they never saw a huge shift in the liquid to ice transition, water to ice transition. But they did see these beam-induced bubbles forming. And when they did diffraction inside of these bubbles, they saw diffraction patterns. They saw crystals, indicating that they either had ice or they had a slurry of ice and liquid, or something of the like. So they actually do have ice in there, which was very interesting. Something I should mention about this that makes it a little bit different from our system is because our system has the ability to flow, we have those flow channels in there. It is less confined than the system that they built, where it, as you can see, there's no flow ports or anything like that. They've got 2 chips, they seal it, and that's that. It's a sealed chip. But let me show this. So this is a video from that. I was excited when I saw this, first off, because it seemed to correlate with what we are getting, but also I saw those bubbles forming too. So that was pretty nice to see that, you know, we have some comparable data that's out there in the literature that matches what we were finding ourselves. So I did do diffraction at one point, this is the image. This is the spot that I took the diffraction pattern from. I do see some spots indicating that there is crystallinity. I actually at first did it on the edge of the window and was seeing the crystal structure for silicon. Don't do that. This here is where we actually have some ice. There is crystallinity. I thought about trying to index them, but then I looked at this phase diagram and realized there are a lot of different forms of ice, different phases, different crystal structures of ice, and they're formed at different pressures and temperatures and things like that. It's a whole rabbit hole I didn't really want to go down, but I wanted to present this data because it would be nice to see somebody else go down that rabbit hole. So basically, all of these experiments, they did what I wanted them to do, which showed me that everything is working, but the answers just gave me more questions. Like, at what point do we see water and ice behave more like bulk? Okay, I had a liquid layer that was greater than 1 micron, but it was still freezing at a lower temperature than 0. Is it that I have to go even thicker to liquid? What about 5 microns? Will that freeze at 0? Is there something else happening? Is it just the liquid thickness, or is it that the cell is pressurizing in some way? What if I completely confine my chip, just like the Hokkaido U paper, and make sure that there's no way for pressure to release into the flow ports? What about contaminants? You could see on one of my slides, the one that I thought was interesting because of the implications for Brownian motion at decreasing temperatures. Those were contaminants of some sort. Could those act as nucleation sites, and can that affect freezing behavior? What about deliberately adding things like salts, antifreeze, etc.? What does that do to the freezing point? What part of cooling rate does, like, what does the cooling rate actually play in the freezing point? That's a variable I didn't control for in these experiments. I was just cooling at different rates and eventually saw something freeze. Well, would the freezing point be a little bit different if I gave it more time to settle at a particular temperature? Potentially. How does liquid flow affect these results? And then, of course, what I think would be very interesting to see one of you guys do at some point is, can you actually control the freezing to direct the final crystal structure of the ice? So that wraps up the ice, the freezing point part of this presentation. Now I'm going to go into copper electrodeposition. This data you've probably seen before in some of our marketing material, but this is just to actually show the plating, since we do make holders for electron microscopes. And so here on the left, we've got 95 degrees. I think it's 95, maybe it's 98. 90 something degrees on the left and 5 degrees on the right. And if I hit play, there we go. You can actually see a big difference in the amount of plating, first and foremost, and the size of dendrites isn't quite the right word, since these don't look dendritic to me. But you can definitely see that there's a lot more plating occurring, and certainly a lot faster in the higher temperature plating experiment than on the right. And some videos here of just that. The left is 50 degrees, the right is -20. Oh, I should have sped these up a little bit, but you can see plating occurring here. The bottom is the electrode, and here is our plating versus the cold. You can see these nice dendrites forming. You will notice, and we'll talk about this in the next section, that there appears to be more beam damage here at the 50 degrees Celsius experiment, even at a much lower dose rate. But again, we'll talk about that later. And something I forgot to mention, instead of cyclic voltammetry here, we actually used chronoamperometry. That is because we wanted to drive the reaction faster. It was going to be way too slow if we did cyclic voltammetry. So one of the things that we changed in terms of our experimental processes, as we got colder and colder, we started driving more and more current and voltage to our system. So likewise, here on the left, we see at 50 degrees C, we apply a negative 0.6 volt potential, versus on the right, when we're at negative 20 degrees C, we actually apply negative 1.5, which is a lot for a liquid cell. But again, you see some plating occur. We don't have any de-wetting or anything like that. And there's clear morphological differences between the two. And finally, on all of these previous slides, I just show one representative curve for each condition. But I wanted to just show this slide to say, like, these curves, there are multiple of them. They stack on top of each other. The data is consistent and it is reproducible. All right, so how are we doing on time, Ninka?
It's okay, but we have 9 minutes in total left also with questions. So if
Go
you
faster. Okay,
yeah,
all right.
that's okay.
Yeah. I was pretty sure I was being too lengthy here. All right, so let's quickly talk about dose. I will mention where I have, you see that we have dose right here. We're actually really talking about electron flux density, just to clarify. And if you'd like more information on this, please see the publication cited down below. And again, as we mentioned, all of the dose that we track in these experiments is by using AXON dose. So one of the things that we thought was very interesting while we were actually doing the experiment was that as we got colder and colder, it seemed like the amount of beam-induced precipitation that was occurring was decreasing. And we could go to higher and higher dose rates, meaning that we could actually have better resolution images because we were increasing our electron dose, that we could go higher and higher without seeing that beam-induced irradiation. Well, I wanted to actually pull that out of the data and see if that was true, right? We saw that behavior, thought that there was a trend with that, but after going back through the data and pulling that information out of it, we see that there is a correlation between beam-induced damage and increasing temperatures and vice versa. Now I'll say a caveat to these slides here. Dose was being acquired, or dose information was being acquired throughout all of these experiments because we have AXON dose and we have those calibrations in. But I was not controlling the experiment in a way that if you were doing a true quantitative dose study to see how beam damage is mitigated with temperature, I wasn't controlling for those variables. So for example, I would have made sure to use brand new spots. You'll see that some of these have already some cumulative dose on them. I would have made sure that we had fresh, so to speak, spots for each of these if I had been doing the study to glean this information, but we didn't. So anyway, sorry, being chatty again. We do see that there is a decrease in the amount of beam-induced irradiation despite having, oh goodness, way higher, let's see, more than 3 times the amount of dose rate, as well as cumulative dose. So I don't label this. The top here is the dose rate, and what you see overlaid on the image is the cumulative dose, meaning the amount of dose at each pixel inside of the image itself. And the top row is time 0, bottom row is after 25 seconds of dose of imaging. And you can see that there doesn't appear to be a whole lot of change in the negative 20, maybe a little bit. Could not find any particles to focus on that, did start growing at -10. At 0, I could find a little one that seemed to grow. And then at 20, we definitely start to see some nucleation of beam-induced damage. And at 50, it was obvious. The next slide, I actually show videos of this occurring. And so -20 is on the left, 50 is on the right, and you can see at the very bottom, the -20 doesn't seem to change very much. The 0 changes a little bit, and the 50, you absolutely see growth induced by the electron beam rather than the experiment itself. Now, this is another thing that I wanted to mention. If the experiment itself had been done with this in mind, I would have wanted to make sure that my distance away from the electrode was identical for each of the experiments. Obviously, because we did do plating, these experiments were from the electroplating that you saw earlier. There is probably a gradient of available copper to precipitate out of solution between the surface of the electrode as you get farther and farther away. I didn't control for that because that wasn't the purpose of this experiment. But if someone were to design a study to really show this, then that's something that they would want to take into account. Okay, some important considerations very, very quickly. Downside to being a development engineer for Protochips and working with the Triton AX system before it was even released was that meant it wasn't done yet. So you probably noticed that some of my temperature slides were not actually synced up with my images, that they didn't have those spots. That's because the software wasn't done when I was doing those experiments. You guys won't suffer from that. But I had to remember how frustrating it is to try and sync up all of your metadata with the individual images and timestamps and stuff like that. Just wanted to quickly highlight how nice it is to have that information already embedded in the PNGs so that you don't have to stress about that, and how nice it is to be able to use this software instead of having to go through and manually sync up the data with the different timestamps. So don't know what you got till it's gone, but you guys won't suffer from this, so we're going to move on. Crosstalk. So Jen briefly touched on this, and I'll very, very quickly just say, anytime that you've got multiple channels, 2 circuits controlling something this closely, you will probably have leakage or talking between those 2, crosstalk. We have to have multiple circuits. We have to have 2 different channels. One is going to control the heating and measure the temperature, and one is for electrochemistry. But you need to be very, very careful to make sure that you're mitigating the amount of leakage that's between those 2 circuits. And this is because we're looking at stuff on the nanoscale, right? Like, which means we're looking at nanoamps, picoamp levels of reaction currents and things like that. So even a little bit of leakage from your heating circuit into your electrochemistry circuit will cause shifts in your OCP, and thus you'll see shifts that are not induced by your reaction itself, but rather lack of isolation between the 2 circuits on the holder. So this was something that it took us a while to run down and to correct, but we did manage to mitigate it with the Triton AX system, and made sure that this is something that you don't have to think about. All right, so conundrum of chemical compatibility. So we already have to field questions about chemical compatibility with our other liquid cell, Poseidon Select. This becomes even more complicated when you add the other dimension of temperature. We are now going from -50 all the way up to 300 degrees C. It's just not possible for us to provide you guys with the information that you need for every single chemical at every different concentration at every temperature, and how that can affect the materials inside your holder or on your chips. So instead, we're going to provide a kit with all of the wetted materials. I put a picture of scrap next to it, even though Jen told me not to call it scrap, to call it wetted swatches. But we're going to have those available to you guys so that you can test your individual sample at your concentrations, at your temperatures, before you do your experiment, to make sure that if you damage something, you're damaging your kit rather than the holder itself. So, all right, finally, future work. I say future work for you, not for me. I already made a list of things that I think would be very, very interesting in regards to freezing and ice. It'd be great if someone could run down the dose effects and do it in a controlled way where they're truly just studying this. particle nucleation and growth, there's so much we could do with that, like people who do nanoparticle synthesis and stuff like that, actually watching that occur at the nanoscale. I did not mention this, the standard reference electrode, but it is an important consideration. First off, even taking out the standard reference electrode from the equation, how does the temperature affect your reference potential on the chip? I would imagine that there is an effect, that there's some sort of potential shift, but I don't know what that would be. But then also, if you're using our standard reference electrode where we have this metal bridge in between the two, if you're heating at the tip, but you're not heating at your electrode, I would imagine that there would also be potential shift between that, but someone would need to study that to confirm it. Higher temperature synthesis, Brownian motion, that it would be great if someone could link dose and temperature to the effects on Brownian motion, corrosion, fuel cells, and so much more. Thank you for listening. Thank you, Yao Yang at Cornell, for the excellent collaboration. Please scan here to register for his webinar. And if you have any questions, please send them now. Thank you.
Thank you so much, Kate, for this lovely presentation, our second half of this entire webinar. We're on our time, but I will take some time to answer a couple of questions if you guys want to stick around, and we can get Jen back as well. Yeah, great. Thank you guys so much. We have a couple of questions, and some of them are a bit more technical. So I'll start off with a first question, and that was the question if the temperature is maintained. So this is about the external reference electrode, actually, that you're talking about, Kate, as well. So how do we deal with the temperature changes that are happening in the holder compared to the external reference electrode, which is on the outside, obviously?
Yeah, so that's actually one of the reasons that's on my slide is I wonder the same thing. It would be the way that I would design the experiment if I were the one doing it, would be that I would have my reference electrode set up. I would figure out what my reference potential is, and then I would cool at the tip and see how much it shifts. And then I would cool the electrode, the external reference electrode as well, and see if that brings it back or if there's any shift at all, because there very well might not be. I would hazard people not to heat the external reference electrode just because I don't know what temperatures it can withstand. You would want to figure that out. But that would be how I would design that experiment.
Yeah. And I think Jen wants to say something as well. Sorry.
Yeah, no, just in case, I interpreted that question a little bit differently. So they'll get two answers and they can pick the one that makes the most sense. I interpreted how's the temperature maintained when the external electrolyte flows into the cell. And so we maintain the temperature in the cell even while flowing via a closed loop control. So we're always measuring the resistance with that heating coil. So if temperature changes, we're detecting that and then we're compensating for it by applying additional current. So just in case the question meant that, there's that answer, yeah. But then you also have Kate's answer with the reference.
And maybe on top of that, to add to that, is that the reference electrode is therefore not being cooled while the tip is being cooled, for instance, and not being heated. So that's something you can add yourself, but that's not something we're doing at the moment. So the reference electrode will stay at room temperature. So then there's a question about crosstalk. The question is, even without crosstalk, do the electrical currents generate magnetic fields that influence the imaging?
That is a great question. Not that I've noticed would be my answer. We still get really nice images, and actually I've imaged dry before, which would be where you would have the highest opportunity for higher image resolution, and thus if there was any sort of magnetic field induced aberrations, that would be the easiest way to see it. So my answer is not that I have noticed the if there is, I mean, I'm sure there's a small electric field being generated, but I think that the magnitude of it is much, much less than what is being given off by the electron beam itself. So the short answer is not that I have noticed.
Okay, great. And then there's a question here as well about the volume changes during the freezing. So the question is, do you need to take care about any volume changes, for instance, during water freezing, so you don't damage your cell or obviously the microscope? So it's a little bit concerned about safety here as well.
Yeah, that is a really good question. So before I did any freezing inside the microscope, I did a whole lot of freezing inside of our pumping station to make sure that I wasn't going to damage my microscope. Not as worried about the cell as I am my microscope, but well, NC State's microscope. But yes, you certainly can if you're not careful. And that's actually why we limit the rate at which you can cool and the rate at which you can heat, is because of just that. If I and I saw this in the high cube, if I tried to cool to the point of freezing any water at 10 degrees C per second, that was too quickly. The liquid doesn't have time to settle into other places, and you do see a spike in pressure, either from the gasket failing or from the window rupturing. But that's why we make sure to limit the rate at which you can cool within the software. But if you are worried about it, I would recommend just do your experiment for the first time on a pumping station. Make sure nothing bad happens, and then do it inside of the microscope.
Yeah, that makes a little sense. And that's also why we try to recommend to first understand all your ex situ results before you do anything actually in situ in the microscope. It can still be in the holder, but maybe not in the microscope to start off
Yeah,
with.
yeah, and just to highlight, I mean, my job is to break things so that you don't. So you know, it's a great question, and I'm glad that it was asked. Hopefully, we've taken all of these things into consideration. But if we haven't, yeah, it's always best if you're worried about it to just test it outside of the microscope first.
Then there's a more generic question, not particularly about the Triton holder, but about the flow management chips. So the question is, have we measured and what is the maximum and minimum thickness of the liquid layer when using the flow management chips? And more importantly, is it possible to obtain meaningful eels data? Because you showed some, how you measure your liquid thickness with eels. So I think that's where that came from.
Yeah, so I have some data where I've done some liquid thickness measurements with the flow chips. That it's not complete. Um, in terms of meaningful data with eels, you actually, if you go to Yao's talk in January, you'll see some really nice data with 4D STEM. It is certainly possible. There are things that you can do, like deliberately inducing a bubble to thin out your liquid layer even more. But the idea with these flow management chips is that you are looking at a thin layer of liquid at the window, even though there are these etched wells around it that allow for a nice transfer of fluid. So.
Nice. And then another question from the same person was, but maybe this is more a question for Jen. I'm not 100% sure. What is the maximum pressure the holder and chips can withstand? Well, with this liquid then.
Yeah, so we don't have an official specification for the maximum pressure, but with the liquid cells, usually the windows that we generate for liquid cells to help prevent bulging are much more narrow than, let's say, our gas system, which allows it also to withstand quite a bit more pressure. I think anecdotally, so don't quote me on this, but just to help you wrap your head around, I know we've done some experiments with pressure-based pumps and such with our system as well, and have applied in a leak check station in that particular situation up to 7 bar with the pressure pump. And so for the windows we were using then and the system we had set up then, the holder is going to be completely fine. It's the chips that will be your weak point, depending on the pressure that you're going up to. But we don't have an official specification. So again, if you're doing any testing with on an experiment, we always would recommend doing it in a leak check station if you're worried about any of the aspects of it. But depending on the windows that you're using, the system can withstand a good amount of pressure, let's say. But always test externally first, just to check, make sure you're not growing anything that's going to poke the windows as well, or anything like that.
It's a great answer indeed. Last question here is actually again a question for you, Kate, but because it's on your to-do list, let's say, or to hope for a list that other people do. I don't know if you know the answer, because the question is there any effect of flow on freezing point of water? Which is a question that you actually posed as well. So
Yeah, I don't know. I would think so, but yeah, I put it on the slide because I also wonder the same thing. So my answer to that would be by Triton, and you tell me.
So basically, start doing research, and we would love to know the answer once you once
That's
you've
right.
researched
That's right.
it.
I will
Yeah.
fully support that experiment. Yep.
Nice. Okay. Well, great. That is most of the questions that we've gone through for you via the chat. We've gone over time as well, and for that, I wanted to thank you all for staying a little bit later with this webinar, and thank you all for attending as well. If you do have any more questions, I mean, there are a lot of things here on the slide. You can contact us at contact@protochips.com, and if you have any ideas for experiments, anything that you technical questions that you have, you can also email Kate, Jen, or me directly. And there's a lot of information on our website as well. Last but not least, it will be awesome if you can fill out the questionnaire that comes to your email afterwards. And again, a certificate of attending will also be sent to your email address. So thank you so much for joining us today. And yeah, please register for the next one on the 14th of January. We're happy to see you then as well. Thank you so much.
Thank you, everybody.
Thank you.